Physical demonstrations. How do we make sounds that are both high and low?
How to make sounds high or low. It's kind of a neat little topic to take a look at. But if you think about a piano or a guitar, if you take, especially a piano, if you take a look at the longer strings on a piano, they're usually the lower notes. And the shorter strings inside the piano, they're the higher notes. And we can show you that with a couple of items. This is a slide whistle. Now, when you blow into the slide whistle, there's a small chamber in here where the air vibrates in there. But if we make that section in there where the air vibrates longer, it makes the note lower. And if I make it shorter, it makes the note higher. So it sounds like this. And you can see how the size of that space in there changes that. And it's easy to remember because they both start with an L. Longer is lower. Now, this is a little a demonstration that you could do at home. You have to be very careful with it, but it's just simply a straw. I like to call this the straw oboe. Now, I flatten this end out just slightly. You can bite on it like this and just pull it between your teeth gently, flatten it out, and then you take a scissors and then you cut a little wedge on both sides like this and like this, and then you blow into this end. Pretty low sound, right? Now, we can change that by changing the length of this tube. Remember, longer was lower. If we make it shorter, it's going to be higher. But you got to be careful.
How do vibrations make sound?
Sound is caused by a vibration. Now, some of you might be saying, what's a vibration? Well, vibration is just something that goes back and forth, back and forth. Now, if the object vibrates fast enough, it's going to disturb the air. And if the air vibrates, our ears are sensitive enough that we can pick that up. Now, to show you what a vibration actually does, we have a tuning fork. And this tuning fork will vibrate at 426 times every second. So when I hit this, these two ends will vibrate. Now it's vibrating in the air and we can't see what the air is doing to us. But our ears can pick it up. So let me just hit this and listen. Now, when it's vibrating, you might be able to see these ends being a little blurry, but you're not going to see what's really happening to the air. But when I take this and touch this to the water, now water is a lot thicker than air, so we're going to see what effect this actually has on water compared to the air. And that vibration actually disturbs the water enough that it splashes out. So we have lots of vibrations going on here, 426 vibrations every second, moving the air. We can't see it, but when it touches the water, we can see what the vibration does to the water. Well, many things cause vibrations. One of the things that's kind of interesting is this cup. In fact, you look at this, and many of you might remember this as the old telephone. If we had another cup on this end, what we would have is a telephone. Now, when your voice vibrates, your voice actually vibrates the air, and you talk into the cup, your voice vibrates the air vibrates the cup vibrates the string, and if we had a cup on this end, this would also vibrate and the person could hear it, so you could talk back and forth to each other. Now, I also want to show you this. This is just a cup with a string in it, and you look at it and you say, well, this is just a cup with a string, but it actually was invented. In fact, this was invented in two places of the world many years ago. In South America, when this was invented, they did it out of like a wooden cup, and they had a wooden stick on here, and when they pulled on the stick, it vibrated and made a sound, and they still use this in South American music. It's called a cueca. Now, with this one, we can pull on the string and actually get the string to vibrate, then the cup to vibrate, and then we can hear it. So instead of using it as a telephone, we're going to use this to create sound. So if I take the string and I pull on it like this, almost makes a breathing sound like Darth Vader. Now we can change how this vibrates because my hand is sliding pretty smoothly on the string. And we can change how this vibrates by using a wet sponge or just getting the string wet. And when I put this on here and pull on here, it makes a different sound. So the vibration now is caused by water being on here, and water lets our fingers slide, and then it catches, and it slides, and it catches. So if I pull on this again, cup can hear what it does. Now, we can make cups vibrate differently. This cup has a special string on the bottom. In fact, it's not even a string. It's a ribbon of plastic. On the ribbon of plastic is actually a lady's voice recorded. And there's little bumps on this plastic. In fact, I can see the bumps in this area. And what this plastic ribbon will say is, "Science is fun." So listen. Did you hear that? Science is fun. Isn't that cool? So I'm vibrating this by pulling my thumb down. It's going over the bumps and actually reproducing that lady's voice. It works like a record.
How does sound make things look better?
So what am I doing? You know, it's hard to figure out what something is happening around somebody, but if you add sound to it, it really changes things. And that's why they spend thousands and thousands of dollars to add sound to movies and cartoons, because sound makes things look better. Now, you saw me just before this, but if we had a little sound, little tiny whistle. See what sound does? Sound makes things look so much better.
What is Bernoulli's principle?
Bernoulli's principle definitely has to do with airplanes. Bernoulli was around about 100 years ago now. He did not invent this. He just discovered it. It was called Bernoulli's principle, named after him. And this is the way I can remember it. It's not exactly Bernoulli's words, but here's his principle. Basically, he said, where there's moving air, there's low pressure. Okay, where there's moving air, there's low pressure. Now, a couple ways to demonstrate that. This is a simple little plastic tube, and in the end I have a Gulf tee. And the Gulf tee has been modified. There's a hole that has been drilled in it so air can come out. Okay, so what I'm going to do is I'm going to take this ping pong ball, which is very light, and I'm going to hold it over that hole and blow air through there. And I want you to watch what happens. Now, that ball stayed up in that column of air, and it stayed in there because of Bernoulli's principle. Now, he said where there's moving air, there's low pressure. Now, the air coming like this hits the bottom of the ping pong ball, and it goes around all the sides of the ping pong ball. So all around the ping pong ball, we have moving air, which is low pressure. And then all the other air in the room around it is high pressure. So if the ball falls one way, the high pressure pushes it back. Falls another way, high pressure pushes the ball back. So Bernoulli's principle works very well in explaining how that works. Now we also have this is a corrugated tube. Now this works together two things, shows Bernoulli's principle and sound also. But this has a corrugated construction, and as air goes through there, the air will be vibrating, oscillating against the sides and making a sound. Now when I spin this around in the air, let me just show you like slow motion wise. If I spin this around in the air, you can see the end of the tube is actually moving through the air. So in reality, we have moving air right here, and where there's moving air, there's low pressure. So then as you spin it around, the high pressure in this room tends to want to fill that void, since some of the air actually goes into the bottom of the tube. Well, as it travels through the tube, it makes a sound, and that's how we can tell air is going through the tube. So here we go. Bernoulli's principle, making a tube sing. Cool, huh? That's Bernoulli's principle. Remember, where there's moving air, there's low pressure.
How does Bernoulli's principle keep airplanes in the air?
Bernoulli's principle, yes, it's hard to understand, but it really is responsible for keeping airplanes in the sky. Now, every time I have done something with Bernoulli's principle, or looked it up on the internet, or found it in a book, they always have a little picture of an airplane flying through the sky. Well, it shows the airplane in a cross-section, and it shows the wings, and the wings are shaped so that the air goes across the top of the wing faster than the bottom. Now, if the air is moving across the top of the wing, and Bernoulli said where there's moving air, there's low pressure, we have low pressure on top of the wing. Air on the bottom of the wing is not moving as fast, and that's high pressure. So it actually gives the airplane lift and keeps it in the sky. Now, to go along with that, we have this little demonstration. It's simply a pen or a pencil, and you tape a piece of paper on there, just like a 2-inch strip, and this is supposed to represent the airplane wing. Now, my breath blowing across the top is going to represent the air blowing across the top of the wing. So when I hold this to my mouth, and it's going to be below my mouth, I'm going to blow across here, and right here we have moving air, and moving air is low pressure. On the bottom of this wing is going to be high pressure, and so this should come up in the air. So if I do this, now you see how that lifted it up? Now, I would really like to do this and show more people, but, you know, then I need a bigger piece of paper and more air, and a bigger piece of paper and more air. I wonder, bigger piece of paper, more air. Let's see, bigger piece of paper, more air. Bigger piece of paper, more air. Bigger piece of paper, more air. Let's try this. Oh! It works, it works. All right, yeah. It works, yay.
How do airplanes stay in the air?
A lot of people wonder why airplanes can stay in the air, and it has to do with Bernoulli. Bernoulli's principle is partially responsible for keeping airplanes in the sky. And Bernoulli said where there's moving air, there's low pressure. Now, this little toy might be able to explain that. This is a little helicopter toy, and it is powered by a balloon. And when I blow the balloon up, when I blow the balloon up, I have air pressure in there, and when I attach it here and I let some of the air out, you'll hear a noise. Now, not only noise is coming out of there, but some of the air is going through each of these blades out this way, causing the helicopter to spin. And as it spins through the air like that, the wind that's going across these wings, like an airplane wing, has to go over the top of the wing faster than the bottom. So if we have moving air going across the top of the wing, moving air is low pressure. What do we have on the bottom of the wing? We then have high pressure, and that's what gives it lift. So let's just try this. And lift off. Bernoulli's principle did it again. Yeah, it's good to know that planes stay up in the air, but and they do come down too because they have to land. Now, all an airplane does when it lands is it loses speed. Air doesn't go across the wing as fast, and it loses its lift, and it starts to come down. And it's coming down because of gravity. Now, gravity is a force between a very, very large object, such as the planet Earth, and anything that's near it, and it will draw it to it. Now, we can kind of demonstrate this with the helicopter. The helicopter will go up, thanks to Bernoulli's principle, and gravity might bring it down. It did. Gravity brought it back down. How cool.
What is a polymer, and how do they work?
Polymers are a fun aspect of chemistry. The word polymer means, poly means many and mer is a part. So polymers are made of many, many parts. And when you mix polymers together, what happens is these parts hook together and form long chains of chemicals, and the long chains of chemicals change the makeup of the substance. Now, what we have today is a polymer that is a white powder, and we're going to mix it with water. And what I'll have to do first is pour the polymer into this cup, and then we're going to take water and pour water into this cup to mix water with the polymer. And then we're going to tip it upside down in just a moment, and we should have snow and ice. So this polymer actually has taken all of that water that was in that cup and combined it within itself, and forms this powder. And this is used for imitation snow. In fact, you can buy this at stores, at various, some even toy stores you can buy this, and they use this for artificial snow. The only trouble with this is it has a lot of water in it, and if you let it sit too long, it might start to get moldy. But it's a fun substance. Now, the other aspect of this is that you can find a powder very similar to this in diapers. It sounds kind of funny, but when inside the diaper, they use this polymer so that when the baby wets, that polymer absorbs all the moisture. So when you take the diaper off, you're just dealing with a heavy diaper, not a wet diaper. And so the polymer is actually, it's a very practical use. They used to use these polymers also to coat seeds. So when you put the seed in the ground, the polymers attract the water, water goes around the seed, and it makes the seeds grow a lot easier.
What is static electricity?
Static electricity, that's a fun one. I'm positive everybody has done this where you've run across a carpeting and you shuffle your feet real fast, and then you go up to a doorknob and you touch it and you get this spark. Well, what's happening is when you're rubbing across the floor, you're picking up electrons. And then when you get to the doorknob and you reach out, the electrons jump from you to the doorknob. Well, there's lots of things that can show that. In fact, if you take a balloon and you rub it on your hair, you've done that, and then you stick it to a wall, it'll stick there. Now, this is a nice demonstration, and you only need 3 things to make this work. You need a PVC pipe, you need rabbit fur, and this is a styrofoam ring, which is basically a material that's used for packing, such as DVDs or whatever. And I cut it into a long strip and taped it together to make a hoop. Now, to make this work, we simply are going to take the rabbit fur and we're going to put a charge on the styrofoam ring, and then we're going to put the same charge onto the PVC pipe, and same charges will repel each other. So when I rub this way, I'm adding a charge to the styrofoam ring, and now I'm going to add a charge to the PVC pipe. They're both the same charge, so they should repel each other. And they do. Look at that. So they're like charges, and they are repelling each other. And so when I hold the stick under there, that tube that it's trying to get away from me.
How do my eyes play tricks on me?
If you feel like your eyes are playing tricks on it, it could be real. Because our eyes will play tricks on us. Some people call them optical illusions. Now, if you want to look at this, I have 2 identical pieces of plastic. And one is yellow, and this one is red. Now, I'm quite strong. So I can actually pull this yellow one from behind and make it longer and bigger. Watch, I'll pull. There. Now, I'll show you. Look at how much bigger it is. I did that. Huh? Now, I'll tell you what, we can put it back the same size. Oh, what? You want to see me do the red one? Well, sure. Here, turn it around, and I'll pull the red one. I'll make it bigger. There. Looks bigger. Let's put it side by side. Yes, it is bigger. Now, do you know what? Our eyes are just playing a trick on us. It's really not bigger, because watch. I put them back together. They're exactly the same size. Okay? Now, if I put the red one down below, guess what? Red one's bigger. If I put the yellow one down below, yellow one's bigger. Our eyes are playing tricks on us because we look at this object as our eyes see it, and they're just turning it around. You could probably do this with bananas too, because they're the same shape. And if I turn it this way, one looks bigger. And if I swing around like this, so can't always trust your eyes because sometimes they're playing tricks on us. Okay, the reason this is happening is because of perception, okay? When we have it like this, you can see, if I turn this around, you can see they're both identical. They're exactly the same size. But when I go down like this, one over the other, the ends, if I can hold this tightly here, this end appears to be short over here and short over here, but when I move it up, it's exactly the same length. Because of where it falls on this elliptical shaped object here, it makes our eyes say, oh, well, look, there's a space there and a space there. This one must be bigger. So our eyes are just tricking us into thinking that this one's bigger, because when I switch it around, look again, identical size, and I put this one below it, we now have that same illusion. And that's why our eyes play tricks on us.
What are forces, and can I multiply them?
A force is a push or a pull. And you know, how can you get more of a force? You can actually multiply forces together to increase the force. Here's a little example of that. We're going to use a couple of tennis balls to show you this. First of all, I'm going to hold this about eye height, and I want you to kind of watch how high it's going to bounce again. Okay, we're going to kind of record that. So I'll start it here, about this high. Try it again. Yep, that's about right. So it was about this high. Kind of remember that. And gosh, I need two. Oh, that's a big tennis ball. Okay. Well, let's see how high this tennis ball bounces. So we'll put this about eye height, drop it. That's about the same, wasn't it? Okay. Yep, just about the same. Now, we're going to multiply the force from this tennis ball, much bigger, into this tennis ball. So when I put this one on top, we're going to drop these together. And when I do that, the bottom one is going to hit the table, and it's going to start coming up, and it's going to apply its force all into this tennis ball. This tennis ball is going to go up. We'll see how high it will go up. This one won't go up quite as high, so we'll watch. Whoa, that tennis ball went. Now this one, it didn't bounce as high because some of the force was this tennis ball was applied into that tennis ball. And that's how you can multiply forces.
How do I divide forces?
Forces are very interesting. One of the things that I'm always amazed at is I've seen people go out onto a stage and then lie down on a bed of nails, and you know, another person comes out and puts a block on their chest, and they hit it with a sledgehammer, and the guy gets up and everything is fine. And it really sounds like an amazing trick, but that guy is really not doing anything amazing. In fact, he's taking and spreading out the force of his body over all hundreds, maybe even thousands of nails. If that guy really wanted to be brave, here's what he should do. He should lay down on a bed of nail, because all of his force would be on that one nail. So I'd like to show you how we can divide forces, and this is a very simple little experiment. I have a copper tube and a wooden dowel, and what I'm going to do is take 2-ply toilet tissue, and I'm going to take and fold it in half, because right now it's single-ply, and now I have the 2-ply, and then on this end I'm going to wrap a rubber band around the toilet paper just to secure it in place. And then watch this feat of strength. I'm going to take the wooden dowel and watch the end right there. Right through! I did that! Right through! 2-ply toilet tissue! Pretty cool, huh? Well, let's change this just ever so slightly, okay? I am going to do it again. This time, I'm going to use 2-ply toilet tissue just like the last time. Fold it in half. Put this over the end, attach it with the rubber band, hold it securely in place. Okay, now this time I'm going to change it ever so slightly. I'm going to be like the guy who laid down on a bed of nails. I'm going to add a bunch of sand. In fact, this little container only was like half full. I'm only going to use about 1/4 of this. I'll pour that in there. And then I'm going to do this again. Now, this time, I'm going to really use some force, okay? Right through the 2-ply toilet tissue. What's wrong? I cannot pop it through 2-ply toilet tissue. And the reason for this is I have sand down on the end. And when my force is hitting this, what's going to happen is it's going to hit that, and then the stick hits a layer of sand grains. That transfers it onto other sand grains. Some other sand grains hit the side. Copper tube's not going to let loose. By the time that force gets down to the end, where the 2-ply toilet tissue is, there's nothing left. And so I can't get through there. So let me just take this out. We'll show you that I didn't play any other tricks on you. Pour the sand out. Try this again. Now, no sand, right through the 2-ply toilet tissue. Pretty cool.
What is Newton's first law?
Sir Isaac Newton, he was born over 100 years ago on Christmas Day, and a lot of people know Isaac Newton for his discovery of gravity. Well, we're going to talk today about Isaac Newton's first law of motion. Now, in that first law of motion, he said when an object is in motion, it wants to stay in motion, and when an object is at rest, it wants to stay at rest until acted upon by some outside source. Now that's a lot of words to remember, so I have to do it my way. This is my interpretation of Sir Isaac Newton's law. I call it the law of laziness. And I say that because things like to keep on doing what they're already doing. If they're not moving, they want to keep not moving. If they're moving, they want to keep moving unless acted on by something else. So the law of laziness. Let me show you just a quick demo of the law of laziness. Now, this is an empty jar, and we're going to place a card on top, just a regular plain card, and you can use a penny, a nickel. I have a little nut here we're going to place on top. Now, if I take this card and get it out of the way fast enough, that nut that's on there is so lazy that it's not going to want to move. So I can probably pull that card out. The nut's not going to want to move. And once the card's out, the only thing it can do is drop into the jar. Now I'm going to move it out of there very quickly by snapping a pen across the card. And that shows you that that is really a lazy object. And actually, heavier objects are lazier objects. Now, I'd like to show you this a little more dramatically because that was kind of fun, but let's do it a little better. Now, I need to set this out of the way. And we're going to use 3 little tumblers that have water in them. Now, I have water in them because the objects that are going to drop in there, I don't necessarily want them to break or break the tumblers. So the next thing we need is a pizza cardboard. Now, this pizza cardboard has 3 areas marked on here, and this is where the tumblers will be. Now, I'm going to line this up so that I have to get down this way and line it up so that they are directly under where I'm looking, and then I want to go this way and make sure that they are under there so that when the objects drop into the containers, everything will be fine. Now, we're going to set the objects on top of these rolled up playing cards, okay? So we'll set those there, and then we're going to use these objects. These are eggs, and these are raw eggs. So hopefully we don't have a mishap and the eggs drop directly into the container below each egg, and maybe they won't even break. Okay, now I tried a number of times, but I can't pull that out fast enough, so I have to use another method to do that. I'm going to use a broom, just a regular broom. I'm going to take the broom and place it on the floor and bend the bristles so that this kind of acts like a spring. Okay, now here's what we're going to do. With the broom in this position, I'm going to pull it back. The first thing the broom is going to hit is the cardboard, and the cardboard's going to go flying, so don't watch the cardboard. Then, once the cardboard's out of the way, this is going to continue, but it's going to hit the table, and the table's going to stop it from hitting any of the eggs. And once the cardboard's out of the way and this is stopped, hopefully the eggs will drop directly into the cups and not break all over. Okay, we'll pull her back. We'll count to 3. 1, 2, 3. Yeah, it worked. Now, I'll show you, too, that these were not just hard-boiled eggs. These were raw eggs. Yes. Newton's first law, the law of laziness.
What is centripetal force?
Centripetal force is an inward pull. It's almost like if you were thinking about a satellite orbiting the Earth, and the Earth's gravity would create this inward pull. In fact, we could use a simple little science toy to demonstrate this. If you take a balloon, this is a clear balloon. You can use any balloon to do this. And if you just go into Mom or Dad's little area where they keep old leftover parts, just grab yourself a 6-sided nut and take the nut and drop it into the balloon. By the way, this is a very inexpensive toy. And then once it's in there, you blow up the balloon. Now, the balloon is going to represent the centripetal force on the nut, and the nut is going to represent the satellite going around the Earth. The Earth would be positioned inside, right in the center of the balloon. Now, once we get this nut moving, it's going to make some noise, and it's going around like this. It is moving around in a circle mainly because the gravitational pull of the Earth keeps the satellite in that orbit. And this balloon is representing the gravitational pull. Now, as this nut rolls around, you notice it makes a little noise. So if we roll this around again, It's making noise because we have a six-sided nut. It's not very smooth, and every time it rolls over one of the bumps, it makes a noise. It's almost like your car tire rolling over the bumps on the side of the road if you get off too far. Okay, so it makes that same noise. Now, we can do the same thing and get a better, take a look at the satellite end with a nickel and a balloon. So we'll put the nickel in the balloon. This increases the value of the science toy by 4 cents, I think. Now, we'll put this in here, and then we'll blow this up. And tie a knot in this balloon. And now the nickel is going to represent the satellite going around the Earth. The balloon is representing the gravitational pull, keeping it in orbit. And as it's going around like this, you can see the satellite, our nickel, going around, and the Earth would be centered right in the middle of the balloon. And the balloon is actually kind of representing the Earth's gravitational pull, pulling it in. As soon as our gravitational pull balloon would break, the nickel would fly off into space.
What is centrifugal force?
Centrifugal force, it's kind of like the opposite of centripetal force. Centrifugal force is the force pulling out. And I guess the best answer I can think of is they used to have devices where they would train astronauts, and they would sit in these little compartments, and it was like being put in a blender, and they would spin around in a circle, and that outward force would actually pull their face back like this and make them really look ugly and strange. But that outward pulling force is centrifugal force.
What is the difference between a solid, a liquid, and a gas?
Solids, liquids, and gases, the states of matter. That's a really neat topic. Now, when you start thinking about solids, liquids, and gases, most of us know what it is. If I mention a brick, you'd say solid. I mention chocolate milk, you'd say liquid. I mention helium, you'd say gas. But sometimes the things are a little kind of mixed up. Like if you think about ice cream, is it a solid, liquid, or gas? You know, when I buy it, I want it to be a solid, but it can change. So states of matter, you can have water as a liquid, you can have it as a solid, you can have it as a gas. And it changes depending upon the temperature. Now, one of my favorite things to use when I'm talking about solids, liquids, and gases is dry ice. Now, dry ice is really, really cold. In fact, it's colder than where I'm from. It is 109 degrees below zero. It is so cold. Now, it is a very strange substance too. In fact, what is it called? It's called dry ice. It's made out of carbon dioxide, but it's got its name from the fact that it never melts. It never ever melts. So it goes from a solid directly to a gas. It doesn't melt, which is kind of neat. Now, since it's going from a solid to a gas, we can show you some things with it. Now, 109 degrees below zero, I'm wearing gloves. I'm not going to touch it because my hands could freeze to it. Now, this is a small piece of solid carbon dioxide. The carbon dioxide is a gas, and you can see a little bit of the smoke coming off. It's really not smoke. This is so cold, it's actually forming a little cloud here. It's condensing the water that's in the air. And it's turning from a solid to a gas, and all sides of it are doing that. The top is, the bottom, the front, the back. So if I set it on the table, it's actually creating itself a little bit of lift, almost like an air hockey table. There's air blowing up from the bottom of the air hockey table, and it lifts the puck up so it floats and it moves really fast. Well, this is doing that too, and I have to just slide it around a little bit, but look, it is floating on its own layer of gas, just like an air hockey puck. And so it's turning from a solid into a gas. Now, we can show you some other things that work with this too. I'm going to need a hammer. Now, I'm going to take this hammer, and I'm going to take and make some of this dry ice into a little pulverized state. So let me just hit some of this, crushing it up into almost rice-sized grains. And then I'm going to take and try and scoop up a little bit of this material. And then we'll take a spoon, and we're going to add some of the dry ice to the balloon. We'll just put some in there. And now, in fact, this could even be called a science for lazy people, because I'm very lazy, and once I get some dry ice in here and I tie a knot in this end, it's going to start doing exactly what I want it to do. So when I tie a knot in there, can you see that balloon? It's actually getting bigger and bigger because the solid carbon dioxide, the dry ice, is turning into a gas. Now this balloon will continue to blow up as long as there's dry ice in here. And this will get bigger and bigger as we just let it sit. And it's turning from a solid into a gas, and the gas that's in there is carbon dioxide. A lot in there yet, so it's going to get bigger. Now, a couple other things we can show. If I take a quarter, now on an old quarter, there's an animal on the back, and that happens to be an eagle. Now, if I take this eagle and I put it on the dry ice, it'll make the sound of an eagle. Listen. Did you hear that? Sounds just like an eagle. Let's try it again. And what's happening, that eagle isn't making that sound, but what's really happening here is the dry ice turning into a gas is causing this quarter to vibrate. Now, I don't know if you noticed when I started, but I held this in my hand a little bit to warm it up. Warm objects make the carbon dioxide turn from a solid to a gas faster. So when I set this down on there, and I'm going to use my hand to show you this, but when I set it down, if my hand was the dry ice and I push down on there, underneath the quarter, that warm quarter, the gas is turning into a gas faster because it's warm, and it rises up and I'm pushing down, and the gas pushes up and I'm pushing down. Well, this is happening very, very, very fast. And when it goes fast enough, it actually vibrates. One more time. Oh, and look what I noticed. This side of the hammer, about the size of a quarter. Now, if we set this down on there, this might just make a sound. Instead of hitting it, I'm going to set it on there. Listen. So it's vibrating. It's also vibrating. I would like to show you that we can make a big cloud with carbon dioxide. Now, if we can get this dry ice to turn into a gas faster, it would give us a lot more cloud. And one of the ways that it actually makes a cloud is with moisture. Now, to cover both bases, to have this turn into a gas faster, we need heat and we need moisture. In this container, I have hot water. So I'm going to take the hammer and I'm going to make some smaller pieces, not real tiny, just break it up into some chunks. And then we'll take these pieces and put them in here and we will make a cloud. Look at that. Whoa! Is that cool or what? Whoa! Look at this. Wow! Look at that go. My goodness. It's bubbling all over. Is that great?